Hello everyone. Today we will discuss about the effect of PD controller and PID controller on system performance. First we will start with the PD controller. So the proportional plus derivative controller produces an output signal consisting of two terms. One is proportional to the error signal and the other is proportional to the derivative of error signal. Already in the previous videos I have explained about how to find the transfer function of PD controller. So that is GC of S equal to Kp into 1 plus Td into S. Okay, where Kp is the proportional gain and Td is the derivative time. So the black diagram of unity feedback system with PD controller is shown in figure. Previous in the videos I have explained about only the controller part. Now we have taken about closed loop system with unity feedback, where G of S it is an open loop transfer function and this is the final output, controlled output, and the R of S is the reference input. Okay, this is our controller. So overall forward path gain is this into this, GC of S into G of S. H of S is 1 here. Okay, so G of S is open loop transfer function, and for the second order system we assume that so this is omega n square by S into S plus 2 zeta omega n, and the loop transfer function it is the product of this GC of S into G of S into H of S, but H of S is equal to 1. That's the reason it is a product of only these two terms, GC of S into G of S. Okay, so GC of S it is the value Kp into 1 plus Td into S into G of S is the second order open loop transfer function. Okay, so this is the final expression for this loop transfer function. Now for this black diagram, we can find the transfer function of closed loop transfer function. So that is a C of S by R of S, that is equal to GC of S into G of S forward path by 1 plus GC of S into G of S into H of S because of negative feedback. Substitute the values of GC of S and G of S in that expression. Okay, so this is open closed loop transfer function. Already we know the values of GC of S and G of S. Substituting in this expression, we will get this. This is the product of GC of S into G of S, and similarly substitution in the denominator also. Okay, after simplifying, we will get this one Kp into omega n square into 1 plus Td into S by, we got these two, after taking LCM these two terms cancelled. So remaining term S into, that is a directly you can take here this part also, S square plus 2 zeta omega n S plus Kp omega n square plus Kp omega n square into Td into S. Okay, now in order wise we can take it here S square and S part, this one, these two terms are S terms, so take it here 2 zeta omega n plus Kp omega n square into Td of S plus last term is this one constant Kp into omega n square. Okay, now here also it is taking here omega n square Kp plus Kp into Td into S. Kp into Td is nothing but Kd. Okay, so that is a derivative control gain. Okay, so from this closed loop transfer function, it is observed that PD controller introduces 0 in the system and also increases the damping ratio. Already you know, this is the, from this only we can find out. From the second order system, you know how to find out damping ratio. That is a, from comparing with the standard second order transfer function, that is omega n square by S square plus 2 zeta omega n into S plus omega n square. When you comparing with this one, you can find out the value of zeta. Okay, that is a damping. That value also increases here, and it introduces the 0 in the system. Okay, the addition of 0, because 0 is nothing but this one. Okay, these are the poles and these are the zeros. So in this case, 0 one term it is increasing, that is 0, and increases damping. From this we can find the damping. The addition of 0 may increase the peak overshoot. Okay, already we know what is a peak overshoot, right? So, and reduces the rise time. We are taking here again in the time domain specifications. What is the effect where it is changing the values of peak overshoot and rise time. But the effect of increasing damping ultimately reduces the peak overshoot. Finally, it would reduce the peak overshoot. Actually, by addition of this one, it increases the peak overshoot. But here, damping ratio also increasing. That's the reason overall when comparing these two, addition of 0 and damping ratio increasing, so overall the peak overshoot is reduced. From the loop transfer function, so that is GC of S into G of S, it is observed that PD controller does not modify type number of the system. Order it is same only. Even in this case it is a second order only S square, and here also it is same. There is no change in the order. That is a type number, so type number of the system. Okay, type number of the system. So hence PD controller will not act or modify the steady state error. It won't change any steady state error by using this controller. Okay. And the last one, that is suitable combination of all three combinations. You can say here the effect of P plus I plus D controller. So that is a proportional plus integral plus derivative controller. So a suitable combination of three basic modes P, I and D can improve all aspects of system performance. Simply saying here, what are the advantages of individual controllers or combining here to get the better performance? That's the reason by combining all the three individual controllers, we can get the better performance of the particular system. Okay, already we know that proportional controller stabilizes the gain but produces the steady state error. Integral controller reduces or eliminates the error, and derivative controller reduces the rate of change of error. So the combined effect of all the three, P plus I plus derivative, cannot be judged from the parameters only Kp, Ki and Kd. Okay, all three are important. Individually they have their advantages. Based on that, if you take all three combinations, you can get better performance of particular system. Now we'll take overall, that is before concluding this effect of individual and combinational controllers. If you are taking P controller, already we know what is the transfer function. It is a Kp. Main disadvantage is so increasing the gain value and overshoot also increases. As the overshoot increases, system stability decreases. That is the main problem. As I, that is integral controller, you know already transfer function is Ki by S. It introduces, that means Ki by S, one pole it is addition, that is also at origin. Type is increased. As the type increases, steady state error decreases, but the stability affects. So that's we need to take care about that. And when you are taking only D controller, derivative controller, generally we won't use derivative controller. It is rarely used or combinationally only used with the P or PI. Okay, purpose is to improve the stability and improve the transient response. Transfer function of that, it is a K, S into K, because it is a derivative. It introduces a 0 at origin because it is a numerator term. That's the reason 0 introduces in the system, and type, it is decreased, but the steady state error increases by using this because it is a rate of change. Individually we won't use because we won't get the constant output. It is always the rate of change of the values. And next, PI controller. Its purpose is steady state error without affection of stability. Because when you are adding PI, it adds pole at origin, so type increases and also steady state error decreases. Okay, it adds 0 in left half of the S plane, so stability is not affected. Basically here, when you are taking this one, Kp plus Ki by S, when you are taking that, one pole is adding, one 0 is also adding here. So that's the reason steady state error decrease and also stability also not affected. That's the reason most of the cases they are using PI controllers. The effects, when you observe, improves damping and reduces the maximum overshoot. Increase rise time also and decrease bandwidth. By addition of this one, PI controllers, it improves the gain margin, phase margin and resonant peak. And this controller filter out high frequency noise also. Okay. Coming to the PD controller. So its purpose is to improve the stability without affecting the actual stability. So transfer function, it is a combination of proportional plus derivative. Basically it is addition of 1 0 only, and that is also in the left half of the S plane. So stability always increases because 0 is adding. So it improves the damping. These are the effects. It improves the damping and maximum overshoot. It reduces the rise time as well as settling time and increases the bandwidth. And it also increases gain margin, phase margin and resonant peak. But by using this, it may attenuate high frequency noise. Okay. So, and the last one, it is a combination of all three controllers, PID. Its purpose is to improve the stability as well as to decrease the steady state error. Okay. So, here it adds a pole at origin, it increases type and also steady state error decreases. If it adds 2 zeros in left half of the S plane, one final 0 is to avoid the effect on stability, other 0 is to improve the stability of the system. Okay, in case it is reducing, and another one it is simply saying improving the stability. That's why, so industries as well as domestic purpose, mainly they are using PID controllers. Okay, so till now last 4 videos I have explained about PID controller, what do you mean by controller, PID individual controllers, the effect of individual and combinational controllers. Okay, next video I will explain numericals, how it affects on the system performance. Thank you all.